In this video, we'll take a brief look at some special sets of numbers and the symbols that we use to denote them, and just a recognition that, yes, there are different types of numbers, right? So the first set, and sometimes you might just see these written or denoted as like a bold N, or sometimes the N will have an extra line there. And this symbol represents what we call natural numbers, right? And what are natural numbers? Well, as a set, it's basically positive integers. So it starts with 1, 2, 3, and so on, right? Now, there's a big debate in the mathematical community every now and again, and it revolves around whether or not 0 is a natural number, right? And most mathematicians will agree that 0 is not a natural number, but don't be surprised if elsewhere you might see that the set of natural numbers listing 0 as an element, right? But for us, we're just going to take basically our counting numbers as our natural numbers, right? The next set up is denoted with, again, either a bold Z or a Z with a line right there, and that is used to represent the set of all integers. Right now, so when you look at integers, these are already integers. In fact, we said that these are positive integers. So the set of all integers now includes 0 as well as the negative integers, right? So how do we denote this? Well, you could start with like a dot, 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 and then maybe go to -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. And in both cases, you notice we can actually list them, so sometimes you can say that these numbers are listable, 1, 2, 3 in order, or, start in the middle and you have 0, and then you go 1, and then -1, and then 2, and then -2, and 3, and -3, and so forth. So in a sense, these are listable as well. The next set is denoted by a Q. Sometimes the Q has an extra line there. And the Q actually stands for quotient, but we don't, some math courses refer to them as quotients, but we're going to refer to these as rational numbers. And basically, a rational number is any number of this form, where it's of the form a over b, such that, so I'm going to describe the form, right? So that a and b themselves are integers, right? And then b cannot be 0 because we can't have 0 in the denominator. So basically, it's a set of all fractions, right? So 1/2, -3/5, 3 over 1, which is equal to 3, and so forth. So rational numbers, or you can simply think of them as fractions, right? But for our fractions in the denominator and in the numerator, we're only allowed to have integers, and of course we can't have a 0 in the denominator, right? Now, we don't really have a special symbol for irrational numbers. But irrational numbers, when you think of just real numbers, a number is either rational or irrational. So essentially, this one, Q complement, would represent all irrational numbers. right? And that's basically, now those are not listable. I could even show you a really clever way of listing rational numbers. And it essentially uses a matrix data structure, and you can sort of list them. But irrational numbers are not listable. So it's basically, these are numbers that you cannot write as a fraction of two, or ratio. Let me use the word ratio of two integers. So what are they, right? If I can't list them, well, I can give you some examples of irrational numbers. So I'll just say, example, like the square root of 2 is an irrational number, right? You can't express the square root of 2 as one integer divided by a non-zero integer. Other famous ones are pi and e and the cube root of 7, and it just goes on, the square root of pi, etc. Right? So again, there's no particular order in which we can list them, but the thing is, and there are formal mathematical proofs that show that this number, for instance, the square root of 2, cannot be expressed in this form, and therefore it's not rational, so it has to be irrational, right? And then, of course, real numbers, and this is an important set for us because the real numbers are the foundation of calculus, right? You need that real line in order to utilize all the properties that are developed in calculus. And what are real numbers? Well, you can think of real numbers as the union of Q and not Q, right? So I'm not going to write it down, but basically the set of real numbers, right? And it's basically the ones that are irrational or irrational. Obviously, they can't be both, right? But the set of all of these numbers that set is referred to as the set of real numbers, right? And for the most part, these are the numbers that we will utilize throughout this particular course. So if I say a natural number, these are the numbers that you should think of. If I say an integer, then these rational numbers are basically your fractions. And then irrational numbers, you get into your roots and pi's and e's and lots more. In fact, there are a lot more irrational numbers than there are rational numbers. Just for completeness, however, I am going to mention one more set, and it's denoted C. And this is the set of complex numbers. Right, and what are complex numbers? Well, they have this form, a plus bi, where a and b can be real numbers, and I is defined as the square root of -1, right? And we will not use complex numbers in this particular course, but I just wanted to give you a complete set. Now, what's interesting is that these sets are not like disjoint or mutually exclusive. If we were to, so I'll just write this as a note, that the set of natural numbers is a subset of integers, which is in turn a subset of irrational numbers, which is in turn a subset of real numbers, which is further in turn a subset of complex numbers, right? So what would be interesting is if you look at the Venn diagram of these, and in fact, let me draw the Venn diagram here so you could see it. Let's just say our universe here consists of just say numbers, right? That's our universe. Well, this would be n, I'll just use a regular n. And then n would be inside z. And then all of that would be inside q. And then all of that is inside, let me undo that. Let's try again. Probably shouldn't have drawn the rectangle. And then let's say that's R. And then what I'll do is I'll just go ahead and label since I didn't indicate any other number set that contains complex numbers, I'll just say that that's our universe, right? So there is this nice hierarchy in terms of number sets that are contained within other number sets. And in other, more advanced math classes, you utilize the properties of these numbers, or in fact, you end up deriving a lot of these properties and showing how one set is used to build another set. So, that like in a real analysis class, you might hear a topic where you construct real numbers, like you actually build them and you see exactly what they are, right? So that brings us to an end to this video. Just wanted you to get familiar with this notation if you've not seen it before. I know some of you have, but it's good to have a nice refresher. And I will see you in the next video.